Hi, this is enolate lecture 5, A and B, and we're going to be talking about alkylation reaction of enolates. So far, what we talked about is how to make enolates, and then we had as an electrophile halogens, and then secondly we had as an electrophile either aldehyde or ketone in a self-condensation or cross-condensation, and then the last electrophile was where electrophiles were esters, and we did a Claisen reaction in same fashion, either self condensations or cross Claisen. So now we're looking at a totally different electrophile, in which electrophile is some kind of halide, alkyl halide, and we're gonna do SN2 type of reactions with enolates. All right. So the overall reaction of an alkylation reaction is very simple. You're going to take an enolate of some sort. It could be derived in any different way. So you're going to have an enolate, and then you're going to react with an alkyl halide. All right. So, for example, we're going to use it as an example. What's in your book? Let's say we have methyl cyclohexanone, and then we're going to use some kind of base to make the enolate. And here we have a choice of making a kinetic enolate or thermodynamic enolate. So let's say we are going to make the kinetic enolate in this case. And so the choice of base that you use is very important here. So unlike condensation reactions, in which for example, self-condensation reaction, in which you wanted to have a mixture of enolate with unreacted carbonyl so that they could react with each other, that's not the case here. We don't want that to happen. So we want this base to be a strong base, so that it quantitatively makes the enolate, and then it goes and reacts with some kind of alkyl halide. So what it does is it does an SN2 reaction at the carbon that the halogen is attached to, and you put on R group where the enolate was. So it's an alkylation reaction. All right. So the strong base that you want to use also depends on whether or not you want to make a kinetic enolate or a thermodynamic enolate, in which case you would make enolate here rather than over here, or more substituted enolate. So the resonance structure would look like this, right? So this would be a thermodynamic enolate. All right. So in either case, you're going to use a strong base. So there's not an equilibrium going on, but you quantitatively, irreversibly make the enolate. So there are two choices. So if you want to make kinetic enolate, use LDA at -78 degrees, because that condition, because this base is very bulky, as we talked about before, and at low temperature, what it's going to do is abstract a proton most accessible, which will be the less hindered one, to form the enolate over here in more accessible place. Whereas if I use a strong base that is small, like sodium hydride, at room temperature or higher, it's going to grab the proton that's more hindered, because it's going to form more substituted enolate, and that's going to be more stable. All right. So once you form the enolate that you want, then you're going to react with an alkyl halide. So in this case, you're going to form on R group over on the other side. So it depends on what you're trying to make. Are you trying to put an R group here or here? And that's how you would choose the two different conditions, all right? So because this is an SN2 reaction, there's a requirement in which, as you know, the Rx should be either our methyl halide, which would be very, very small, or primary Rx, okay, not secondary or tertiary Rx. And the reason for that is because we want to promote substitution reaction in which you have by mechanism SN2, so you want the carbon that the enolate is attacking to be as accessible as possible and make the leaving group leave at the same time. If that is not the case, like if you're trying to react with the secondary or tertiary halide, what's going to happen is you're going to have a competing reaction, and the competing reaction will be an E2 elimination reaction in which the enolate will serve as a base and grab a proton rather than displace the halide. Okay, so we don't want this competing reaction to occur, and that will happen more and more if you have a bulkier and bulkier alkyl halide. All right. So that's sort of the requirement for doing alkylation reaction, that you want to use a strong base, number one, and determine which base you want to use. And number two, the other requirement is that the Rx has to be either primary or methyl halide. All right. Notice another subtle point that you see here is that one, in this case over here, when you make the enolate over on this side and you attach an R group, notice the center that you make, right? The carbon bond that you're making. So this carbon is now a chiral center, right? Because it's got 4 different things on there, unless R group is a methyl. But if R is not methyl, then it's creating a chiral center here. So because you're going from a flat intermediate and then you're reacting with the Rx, the enolate could attack the R group either from the top side or the bottom side. So what you're going to get every time you do chemistry of this sort, you're going to get a racemic product at the center. Okay, so you have to keep in mind, if you started with a chiral center, for example, over here, and you make an enolate here, then you're destroying the chiral center by making this double bond. And then obviously over here, which is chiral center, when R is not CH3, once again you're going to make a racemic product. All right, so every time you go through an enolate, unless there's something special going on, for example, having like a chiral auxiliary or chiral enzyme or chiral catalyst, the alkylation reaction will proceed to give both the R and the S at the chiral center that you're creating, so that you are getting a racemic mixture. Okay, so this is a very simple chemistry. You should be able to form an enolate from the reactant below. And so tell me what kind of enolate you're making, and also tell me what base you're going to use to form the enolate. And then each one of these, you're going to react with this Rx, ethyl iodide, and give me the product for those. All right. Probably after you do that, you should be able to do the other alkylation type of reactions. And the other alkylation, there are 2 special alkylation reactions. One is called malonic ester synthesis, and the other one is called acetoacetic ester synthesis on the next page. Those are special named alkylation reactions, and the reason for that is it's pretty well known. Chemistry is used often and you'll see the reason why. And but basically, if you understand this chemistry here, there's really nothing unusual about the chemistry that we're about to look at. Okay, so let's look at the malonic ester synthesis first. And basically the overall transformation that you're making is you're going from some kind of alkyl halide, and the halide leaves, and in its place you're adding basically acetic acid. So this is the part that you add to the R group. That's the overall transformation. Okay, so the reason why it's called malonic ester synthesis is because this right here is a malonic ester. And that's the starting material, which is very easily purchasable. So then this malonic ester, the reason why it's a good starting material to start is because notice this has two double bonds and it's got the carbon in the middle. So because of that, you know that the pKa of this hydrogen is like around 9. It's very easily formed by, you know, pretty weak base. So you would make this from malonic ester. So the malonic ester is, you know, with the two hydrogens here actually. So after you use sodium ethoxide, you will make this enolate. So once you make this enolate, then you're going to alkylate with Rx. So then you're going to alkylate it at this carbon. Okay, so this chemistry is exactly what you looked at up here. So it's basically an alkylation reaction, right? So once you've alkylated, then the rest of this is sort of a additional chemistry, which takes advantage of the malonic ester. So you're going to take the malonic ester. So this is the second step. So this is the first step. And this will be reaction 2 of this multi-sequence. So you're going to take this product and then you're going to do a hydrolysis of ester by cooking it with acid and water. And notice that you've made the ester into acid, and you should know that chemistry. And then what happens next is you take the product of that, which is beta carbonyl carboxylic acid, and you're going to heat it. And what happens is then you decarboxylate. All right, decarboxylate or remove CO2. So how it does that, this is the mechanism, and we went over this already, of how the decarboxylation works. So we went over this already, but basically it forms this 6-member transition state in which the proton is removed, and then it does this concerted reaction in which the carbon dioxide, this part, basically leaves, forming this enol, and then that tautomerizes to the product. All right, so I'm going to stop here and continue.